Thank you for this very kind invitation. It's a great honor for me to be here for this keynote. When we were trying to find a title for the presentation, we were discussing with Vikas, and we thought, well, maybe something esoteric, statistical. No, maybe something melodramatic, like we are all doomed. No. You know, he said he wrote that paper in memory of David Sackett, and the title sounded pretty nice. So, evidence-based medicine has been hijacked. Much of what I'm going to talk today is material that is also contained in that paper, but probably with a little bit of a different tone sometimes. So, right when evidence-based medicine was starting with David Sackett and Gordon Wyatt, who gave the keynote yesterday, there were lots of non-evidence-based medicine tools out there. So ex cathedra pronouncements by prestigious opinion leaders, like me. Editorials, like those that I write all the time. Non-systematic reviews, professional society guidelines done for the glory of the profession. Pamphlets from drug reps, and other marketing material that was disseminated in medical or so-and-so called scientific meetings. Now, things have changed over time. Evidence-based medicine has been very successful. So in 2016, these are the new key tools of non-evidence-based medicine, still splendidly serving vested interests. Practice guidelines based on seemingly rigorous processes. Systematic reviews and meta-analyses, my fond type of design. Randomized trials, wonderful marketing tools. Observational studies and risk factor epidemiology. You cannot dream for anything better. X-omics, predictive medicine, precision medicine, personalized medicine, individualized medicine, stratified medicine, subgroup medicine. I didn't call my contact at NIH to ask what was the term for this month's submissions, but I need to check on that. And physicians, you know, all of us, we're wonderful marketing tools for non-evidence-based medicine. This is my sad realization, as I stated in that paper. EBM is widely tolerated only when it can produce mostly boring evidence reports that can be endorsed by experts and or serve vested interest. And the very same people who were previously spitting when mentioning EBM or meta-analysis or systematic reviews are now using the very same term to buttress their eminence-based medicine claims to prestige by misusing the tools of EBM. So how good is the evidence after all these years of focusing on how important randomized trials are and how important systematic reviews and meta-analyses are? We have all done our best in that regard, and this is how it looks. Along with several colleagues, we tried to look at systematic reviews published in the Cochrane database of systematic reviews, a wonderful initiative, as you all know, over a year and a half. 1,394 systematic reviews that we assessed. We looked at the grade summary of findings performed, and 600 of them had grade assessments. The others that didn't, actually, there was a reason that they didn't. Most of them just had very little or no evidence practically, or very, very poor quality evidence. Among those that did, so they thought that, well, there's something here that maybe we can try to assess. The quality of the evidence for the first listed primary outcome was high in 1 out of 8, roughly, moderate in 31%, 31% low, and 24% very low. And even when all the outcomes listed were considered, only 19% had at least one outcome with high quality of evidence. Of the reviews with high quality of evidence, only 25, so we're down to 25, starting from close to 1,400, had both significant results and a favorable interpretation of the intervention. What I'm telling you here is what you see every day. You go to the Cochrane database because it's the best tool that you can have to see what evidence we have. And usually what you see is we have no evidence or we don't have good evidence. We don't really know what to do. This has been a long-standing problem. More than 20 years ago, Frankel and West showed these very nice data about uneven research evidence. For spongiform encephalopathies, there were at that time 2,000 Medline papers per 1,000 patients. Each patient was dying, taking 2 papers to the grave. And for myasthenia gravis, 156, cerebrovascular disease, 7.7, severe varicose veins, a very common and major problem for many, many people, really no papers. It was not very molecular sounding, so why work on that? Several years later, we looked at the entire randomized evidence that had been done in sub-Saharan Africa to try to see how much randomized evidence we have for what accounts for 25% of the global burden of disease. We found about 1,000 trials, which is 0.1% of the randomized evidence globally for 25% of the global burden of disease. Actually, it was even worse than that, because most of these trials had been done for conditions that pertain mostly to Western populations and the ailments that people like us would suffer from. But they had to be done somewhere, so they were done in sub-Saharan Africa. Science is making progress. Biomedical science is making even more progress. And this means that we have millions of discoveries. A few weeks ago, we published that paper where we text mined the entire PubMed since 1990, and also close to 1 million full-text papers, and we found that 96% of papers that report p-values show statistically significant results, both in the abstract and in the full text. So discovery, all of these papers say that we have found something significant, and usually it's something new, or quoted to be new. Significant discovery has become a boring nuisance. We've just had so much of that I just don't want any more. Please, I don't want to make any more discoveries. Can we get any of these discoveries to work for us at some point? Well, do they work for us? Some of them do. Clearly, we have made progress. We have more interventions than we had in the 19th century or even 10 years ago. But the time it takes to make that progress is pretty long. So looking at the most highly cited papers in the history of clinical medicine, those that got more than 1,000 citations from other colleagues, the average time to get to that milestone, which is shown by the red lines in that schematic, from the first discovery, from the first description of the discovery, was on average about 25 to 30 years. And in some cases, like nitric oxide, it took about 200 years. When it was first discovered, very soon someone tried to experiment on that. Richard Daly tried it on his own self as the experimental animal and almost died, and then let it aside. And it took 200 years for the discovery to materialize. Even when these discoveries materialize, about 40% of the time, even when you get to that point of having the creme de la creme evidence of a study that's extremely heavily cited and has major impact in the literature and on practice, you see some black lines in about 40% of the cases, which means that there were other larger studies or better controlled studies that showed that that intervention actually did not work, and we were misled to think that it works. Who's doing that research? Well, currently, we're happy to let the industry do most of the randomized trials for interventions that have the highest chance of working. I mean, if you believe that homeopathy works, I give up. Maybe I'm at the wrong audience. But if you believe that, yes, there should be some classic science behind interventions, then probably you expect that drugs and biologics and these type of technologies should work. But then, who is going to test those? The paradigm is that those who manufacture them should test them. And this is what clinical research looks like. It's these auto loops. Let me try to guide you through that weird picture. If you see a node, a blue node, this is a company. And there's 15 companies who publish the largest number of trials that they sponsor. If you see a link between the nodes, then this means that there are trials that are co-sponsored by two companies, and they look at products that both companies have. So you see that there's very thin connections, and usually there's no connections, which means that companies do not risk the chances of comparing their manufactured products against competitors. There's one exception for Sanofi and BMS in that figure because they have co-manufactured one drug, and this is the only reason why that shows like that. But practically, the autoloops, their thickness is proportional to the number of trials where the company is only dealing with its own world of products. So no matter what the result is for that trial, practically the company has a very good chance of saying that something about their manufacturing world works and they're building their case for better marketing. This is real. This is looking at even head-to-head comparison trials where there are drugs by two companies involved, different companies. And we looked at that recently along with Maria Elena Flacco and other colleagues. We found that 55 out of 57 such trials concluded favorably for the manufacturer. Success rate close to 97%. I would say we can skip that step. Why do we need these trials? We can just make sure that they do work, and let's move to the next one. How about meta-analysis? Well, meta-analysis supposedly can help us look at the big picture and therefore sort out some of these potential biases. So let me start from meta-analysis done by the best meta-analysts in the world who have no conflict, they have the best intentions, they have the strongest methodological background. They're the people who teach the courses of meta-analysis. They're my friends. The meta-analysis that I compare here are done by these people. And I'm just comparing network meta-analysis for antidepressants, showing the ranking for different antidepressants in these different network meta-analyses. And there's practically absolutely no agreement. One drug is the best in one ranking, and it's the worst in another ranking. Paroxetine and sertraline are classic examples that go from the very best to the very worst among those being ranked. What's wrong with that? Well, here you have the best of the best, but there's still so many steps in a meta-analysis and so many decisions that need to be made, and they're made after the fact, they're made after the data are available out there, that you can get very different results. Now, let's change gear and let's go to a situation where maybe you don't have the best methodological experts in the world, and maybe you don't have people who have no conflicts of interest. Here's another set of meta-analysis on depression. We looked for meta-analysis on antidepressants for depression published over 6.5 years. And we started searching after 2007 because this is when the big debate about antidepressants increasing the risk of suicide and suicide-related death arose. So we wanted to see what was the response of the meta-analysis world to that debate about antidepressants being effective, safe, not effective, who knows. We found 185 eligible meta-analysis published over these 7 years. It was a factory of meta-analysis. 54 of them had authors who were employees of the assessed drug manufacturer, and close to 80% had some industry link, sponsorship of authors who were industry employees or had conflicts of interest. So a real factory of meta-analysis, more than 20, 25 of them published each year on a very similar topic. And what do they conclude? Of the 185, 58 had some negative statement in the concluding statement of the abstract. But if you were to look at the meta-analysis that had industry authors, 53 out of 54 had absolutely no caveat about antidepressants in their conclusion. Conversely, those that did not have industry authors, the rate was 44%, and those that had no industry involvement, the rate was over 50%. Now, I'm not sure whether that one team of industry authors that mentioned some caveats are still employed by that company, but I need to check. So really the interpretation and the final conclusion, which will be what a clinician will take as the take-home message, can vary enormously. Then you have guidelines, which are another valiant effort to try to put some order into that chaos, taking randomized trials and systematic reviews and meta-analysis and trying to get the best minds and the best experts and hopefully unconflicted people to make some decisions. How often does that happen? Unfortunately, very rarely. Along with Ginny Lenzer and Jerry Hoffman and Kurt Furberg and many other colleagues, we wrote that paper in the BMJ where we suggest that you can have a system of red flags for guidelines that will tell you that maybe you need to start being a little skeptical about what you read in that guideline. And if you look down that list of red flags and you go to any random guideline that you can pick from the literature, it's very likely that it will have at least one red flag, and it's highly likely actually that it will have multiple red flags that would immediately create substantial skepticism. Transparency and reproducibility. This is a front that is expanding very rapidly. There's lots of discussions about how we can make research more transparent. So if we have the raw data available, we can go back and recheck everything. Well, if we have time, but we'll find out. Or if we have the expertise, or if we can understand what these databases are, or if we have the source code, or if we have the software, or if we have other resources that we need to go back and check what was there. But how often is that happening? Recently, we randomly sampled PubMed, 500 papers from the last 15 years, and 259 of them had empirical data. So we asked how many of those have all the raw data available. The answer, you can probably read the abstract, but anyone wants to bet closing their eyes if they haven't read the paper? Out of 259 papers, a random sample from the biomedical literature, any guess? One? Any better bid? 5? So 0. So none of these papers had all their raw data available. How about the full protocol? Any bids for that? And I've made you pessimists. There was one that had a protocol available. And actually, that was a paper. Because how would you incentivize someone to share the full protocol? It's a full paper that you can publish with a full protocol. So in large scale, this is not happening, and it's not easy to happen. Sharing data, there's lots of obstacles that need to be overcome. It takes time, it takes resources, it takes communication, it takes a change in the incentive structure of why are we doing research. It takes a change also in the level of trust that we can have and in the level of engagement that we can have among investigators, sponsors, funders, and other stakeholders. When that does happen, we can reanalyze the data. So this is an empirical evaluation where we looked at reanalysis of randomized controlled trials that had been done and published in the literature, focusing on the very same PICO, the same clinical question as was the original study's aim. And we found 37 such. I'm sure that we missed some because it's not easy to unearth these papers with any search strategy. But among these 37, 35% of them concluded in an entirely different conclusion mode compared to the original paper. So asking the question, should patients be treated or not, the answer was different. Or who are the patients to be treated? The type of patients was entirely different in the original and the follow-up. Who did these reanalysis? One might think that maybe they were rogue reanalysts trying to get some glory out of coming up with a contradictory statement, or people who didn't know how to work with the data and they misinterpreted some variables or who knows. Actually, almost always, it was the same authors who had published the original paper. What that means is that the original authors, 35% of the time, came out and gave a completely different conclusion about what their trial meant in the reanalysis. And why is that? Probably my explanation is that this is just the tip of the iceberg. I think that many more reanalyses were done. Probably most of those didn't show anything that was different. But the current incentive structure in science says that in order to publish, you need to say something extravagant. You need to say something new. You need to say something different. You need to say something confusing. So that's what they did. They confused their own trial, more or less, to try to come up with a new statement that would be publishable. Containing the influence of conflicted stakeholders and authors is clearly desirable. But how do we do that? Is transparency in potential conflicts of interest enough? If we just report conflicts of interest, is that sufficient? Or do we need more stringency? For example, who should be the sponsors and who should be the authors of sensitive studies like randomized trials, like meta-analyses, like cost-effectiveness analysis, or like guidelines? Can we allow people who are sponsoring or manufacturing a specific technology to be the authors of these papers? Eventually, who should fund research? This is an open question. And here I'm trying to juxtapose what is currently happening versus probably what would have been ideal. So currently, if you divide research in 3 categories, discovery or blue sky, applied preclinical research, and clinical research, public funders fund preclinical discovery, blue sky science. And for blue sky science, I think this is legitimate. This is wonderful. Curiosity, scientific curiosity, coming up with ideas that we have no clue how they might work in the future. You cannot promise any deliverable. Writing grants and promising deliverables is completely counterintuitive to doing this type of discovery research. If it's discovery research, it cannot have deliverables. You can say that I will do my best, I will work until 3 o'clock after midnight every night, I have these wonderful credentials, my IQ is 250, please fund me, but you cannot promise that you will cure cancer. If you're going after deliverables, if you say, I'm going to deliver that particular drug or that particular test, then why should public funds fund that? I would say private entrepreneurs, the industry, people who want to take that and move it forward and make money eventually and save lives, they should do it. And then you have clinical research or evaluation research where you want to test whether that new developed drug or test or whatever does work or not. And here, you need non-conflicted stakeholders. You need public funding again and people who don't have a conflict of interest. It's almost the entire opposite currently. There's a little bit of funding for blue sky research, completely compressed all the time. Most of the NIH funding goes into applied preclinical research with deliverables, and almost all clinical research is done by the industry, with some exceptions. Let me cover a couple of points also about observational studies. I've talked a lot about randomized trials and their rippling effect through meta-analysis. So lots of people believe that we can do far more with observational data sets, and I'm not really a believer. This is a field-wide view of one field of risk factor epidemiology. It's risk factor research for pterygium, which is an eye condition. And what I have plotted for you here is the 60 studies that have been done and the factors that they have studied. There's not 2 studies that have looked at the same factor. Everything is a little different from everything else in terms of both the factors selected and how they're modeled. This is why you have these different colors. What are we going to adjust for? Well, there are some risk factors that everybody in the field agrees that they are important. And these are the 10 factors shown with the pink color. And this is a sample of the studies that have worked in that field. And there's not 2 studies that have looked at the same adjusting risk factors. Even though everybody says these are important, nobody considers all of them, and nobody considers even the same subset of those that we feel are important factors. So what happens in that situation is that you get what I call the Janus phenomenon. Janus was a Roman god, and he was the god of thresholds, or you can see how you can pass a threshold of significance. He was looking both sides of the way in thresholds, so in both types of results were possible. And this is what observational epidemiology is about. Any result is possible. What I'm showing here are clouds of results that contain about 1 million points of different results for the very same association being tested each time. I'm just testing, for example, in the far right, whether alpha-tocopherol is associated with the risk of death in the National Household Survey data. And how do I get 1 million analysis? Well, if you start thinking about what else might affect death risk, age does, gender does, Exercise, probably. Chronic disease, heart failure, There's many, many other factors that you can start entering in the model, but for each one of them you can choose. Should I enter it or not? So you have 2 choices, times 2, times 2, times 2, times 2. If you do that for 19 variables, you go up to 1 million. And then, if you plot the hazard ratio on the horizontal axis and the minus log 10 p-value on the vertical axis, you get that V shape eventually. The V shape means that on the left-hand side are the results where alpha tocopherol decreases the risk of death. On the right-hand side are the results where alpha tocopherol increases the risk of death. You can also get significant results, very significant results. Just ask me what you want to get. I'll get it for you. So it's just very easy. You can do it even regression model, and let alone adding then subgroup analysis, interaction effects, different modeling options, censoring, time follow-up, missing data, and so forth. So risk factor epidemiology in public health in 2016, this is my summary. Major risk factors remain highly prevalent. For example, smoking, we know, unless we do something, it will kill 1 billion people in the next century. Epidemiologists like myself are addicted to pursuing massive amounts of insignificant, significant results. I have so many databases, I cannot do anything about it. I'm addicted. I will go back to my hotel room and I'll start cranking chi-squares, I promise. There's no way I can avoid that. And salami slicing, data dredging is the norm. This means that public policy is dictated from spurious evidence. Is that all? Well, it's even worse, because we have even more data. We have big data, which means that we can proliferate discoveries, but are mostly false discoveries because they have very low priors, and the mere massive amount of results means that we can get p-values of minus 10 to the minus 100 that mean absolutely nothing. Ala malas kilis skopelo peplimenon oka nia parex elan epi polyferteron estin exetarus en ni pothimene I ama pandas. What is that? Anyone? My goodness, I belong to a dying civilization. I'm Greek. I owe so much debt. Well, I'm also American, but I also owe lots of debt like that. So this is Homer. This is from the Odyssey, and Circe is telling Ulysses that hug Scylla's crab, sail on past her top speed, better by far to lose 6 men and keep your ship than lose your entire crew, because you have Charybdis on the other side, which is a whirlpool and will just sink the entire thing. So there is Charybdis as well. Multiplicity of Scylla with the multiplicity of analysis is dangerous, but you also have private corporations sponsoring the construction of doubt about the adverse effects and toxicity of their products. You have quacks ranging from television presenters and movie stars turned into health trainers. You have pure science denialists, for example, climate, HIV, vaccine denialists, religious fundamentalists. So there's even worse that can happen, I think, to science and medicine. And then you also have some entrepreneurs and some innovators who even think that science and the scientific method are obsolete. Like Wired a few years ago said, the end of theory, the data deluge makes the scientific method obsolete. And about a year and a half ago, I published a paper because I came across a company that was the highest valued startup currently with $9 billion. And I said, wow, that's great. They're promising to revolutionize medicine and disrupt everything that we do. I want to work with them. But I couldn't find a single paper. And that was stealth research. And then there were scandals in Wall Street Journal and the Department of Health claiming that what they do might be killing people. So how do we steer clear? We can steer clear if people who practice medicine, who practice healthcare, do care about patients and their outcomes. So this is what EBM should have been all along. This is what David Sackett said. Evidence-based medicine is about integrating individual clinical expertise with best external evidence. But unfortunately, what happens is that clinicians are under tremendous market pressure. Most discussions in department meetings are about money, and this is mostly becoming finance-based medicine. Clinicians are incentivized to capture the largest possible market share, to satisfy customers, to get high satisfaction scores, to charge more, to perform more procedures, to tick off more items on charge forms that then come to me as a health services researcher, and I analyze them and publish papers. A logical consequence: how likely is it that physicians will design studies that threaten their jobs, decreasing the procedures, testing, and interventions that they do? Is EBM doomed to be heartily accepted only when it leads to more medicine, if this means less health? To conclude, I don't know whether antidepressants work as they're supposed to, but please don't take them unless you have major depression. Science is still the best thing that has happened to human beings, and I think that well-conducted research is the key for securing and enhancing the future of mankind. Evidence-based medicine is a wonderful idea. It has always been a wonderful idea, but unfortunately, its tools and its results have been hijacked. We need to think more about what makes clinical research clinically useful, and perhaps try to re-engineer the reward system to align it with production of credible, useful, unbiased results that can help humans. Eventually, EBM may still be possible to implement somewhere, someday. These are some of my colleagues who have tolerated me over the years. Thank you for tolerating me for 30 minutes.